Hi, this is a lecture on Newton's laws. This is particular relevance to whatever we're going to study about the ideas of systems of particles and rotations in more relevant to CBSE class 11 chapter 7. But before that we need to look into Newton's laws. I might get a bit detailed on this, maybe this will run for about half an hour or so. But trust me, whatever you learn from this, whatever ideas you gather from this on Newton's laws is fundamental to whatever statement we are going to make further down the line with respect to motions of bodies. Okay. Now we go to Newton's law, the why of Newton's laws. Newton's laws of motion. So these are the fundamental principles on which the whole foundation of classical mechanics or even classical physics rest. It tells a lot about motion, about movement of matter in this universe. So whatever movement we observe in this universe, whatever we see in this universe, we routinely observe a lot of movement in the universe, isn't it? This movement is of very simple nature, like what we observe in a domestic scene. For instance, if you look at your room, you may happen to see some kind, maybe a chair at a corner or a refrigerator here. A refrigerator and a chair at a corner of the room, and maybe a ball rolling in from the doorway across the floor. And as you observe, sit in the corner and observe and see what's happening here, you probably will notice that the ball rolls down the floor at probably a bit higher velocity as it enters from the doorway, and then it progressively slows down as it comes to rest some corner of the room. And you may also observe with your everyday senses that the chair and the refrigerator is at rest. So this is what has been happening. And observation, all modern sciences, more particularly physics or chemistry and the natural sciences, they rely a lot on observation. So when you say you observe something, when you see something, you perceive it with your senses. You probably see it, you hear it, and you can feel it by touch. With your five senses, when you observe something, then that's entitles you to consider something to be true. So observation, a lot of physical phenomena, whatever science that we are propounding, whatever phenomena we are explaining should be observable and could be observed multiple times. If I can show you that thing happening in an open forum, then it's that will be a sufficient that will be the what do you say, a sufficient establishment of the fact of such phenomenon. So it's about observation. So I observe and I could reproduce such an observation to any interested viewer. So here, so that's why we dwell a lot on observation. So this is to do with observation. So you observed that in your room, sitting in your room, that there are some things at rest and there are some things at motion. But whatever we observe in our domestic life or day-to-day life, they have a lot, they are not simple phenomenon. They are not simple scientific phenomenon. Now, whatever I mean by simple carries a lot of weightage here. You don't mistake it as being something not so important by the word simple. It's the elementary scientific phenomenon. Whatever you observe is mostly compound phenomenon happening. So whatever we observe in our day-to-day activities is more of a combination of a lot of scientific phenomenon working together and producing a result, or rather a consequence of a lot of things happening together to give you a result. See, for instance, the ball here. So what makes, when you say that your observation over the years using with your common sense, you may probably very well reason out that once the ball enters the room at some time or the other, it's going to come to rest. That's because the ball is going to lose energy There had been some energy applied to it, some force has been applied to it that causes it to enter the room from probably somewhere on the street, but it's going to consistently lose energy. And this loss of energy is a compound, a great combination of a lot of phenomenon. The first of such would be the friction of the ball against the floor. Even if it is the most precisely polished substance, under the microscope it looks something like this. It would look extremely rough. So what happens here is, it would look extremely rough under the microscope. So what happens here is, the surface of the ball goes on against, tries to push against the irregularities on the surface of a polished surface, such as even a tiled surface. And these microscopic irregularities cause the energy to be lost as it rolls down the floor. So there is friction involved. And there is wind inside the room, air inside the room, and the surface of the ball again has to make its way through the air. So that's again friction. Friction with air. And what else? There is a deformation of the wall of the ball. There is air inside the ball, and it's a thin wall. Probably it's very tautly inflated. That doesn't matter. Still, there is bound to be some kind of a deformation of the wall of the ball as it weighs down on the earth, as it weighs down on the subjected to the gravitational pull. It deforms here, and then some of the energy is lost. So that's deformation of an elastic body, however least elastic it is. And inside the body are molecules of air. And what happens by this deformation is that the molecules which are already in random motion, a lot of chaotic motion, what we might call the Brownian motion, now gets induced to move furthermore agitated, causing its temperature to rise. So there is some of the energy getting lost as temperature increase, or thermal energy. So it's a conversion of mechanical energy to thermal energy. So these are all very separate and very clearly understood phenomenon, very well established phenomenon in their own rights. But we are unable to observe all this with our naked eyes in a day-to-day manner, in our day-to-day observation with our senses. What we see is a consequence of all these phenomena acting together and producing some kind of a result. And that's not good enough if we want to make conclusions of more complicated nature. We would need to look at the individual rules and make sure how each one of these work. And not the least among them is the nature of motion itself. And motion assumes a lot of importance because the universe is in a state of nothing but motion. Everything moves. Everything, without exception. For instance, you observe that this chair is at rest, but actually what happens here is that, or this refrigerator is at rest, but there is a minute vibration going around here because of the electrical motor that's running inside the refrigerator. And any house or dwelling here inside which you keep the refrigerator, that's going to be deflected to a minute set into a minute oscillation by the wind that flows, or the surface of the earth is shaken by thousands of small tremors every year, every day. So every given second, there's going to be some kind of movement of the earth's surface. A very small movement. It's not an earthquake outright. It's a very small movement. That's again going to shake the foundations of the building, and the fridge is going to move a little bit this way or that way. And so that's happening all the time. And again, if you deduce it further, if you look at the surface of the refrigerator and get it down to the level of molecules, all molecules, notwithstanding whether they are solid or liquid or gaseous, are prone to movement. The only difference is that crystalline solids move about their mean positions. They oscillate very fast about the mean positions. So there is movement everywhere from the molecular level. Now zoom it out further out. See, this house is here. That moves because of the tectonic plate. That itself is a pretty major, a large force. But again, this planet itself is not at rest. Whatever planet, Earth, on which this house sits, it's moving around the sun at great velocity. It's rotating around itself, and it's even wobbling about its axis. That's causing the seasons. So you have movement all the time, and observing the nature of motion itself is going to be a very important thing when you go to start with physics. So how do we deduce this motions? So how do you try to separate out all these phenomena and look at motion itself separately? Can we use sophisticated equipments? One thing that helps us to observe better is the use of technology to make better observations. For instance, you have a microscope to observe things that are happening at a very small level, and a telescope, a light telescope. A simple light telescope will help you observe something. You can gaze at stars and planets. That happened maybe since the time of Galileo in 1450s or 1460s. So this has been a popular thing, and these telescopes have evolved further. Now we have large-scale observatories relying on radio telescope. We don't even use light waves to do the observation. We use radio waves. We use laser beams to make observations. We have observatories that can with the help of computers can correlate data of two observatories situated maybe 3,000, 4,000 kilometers across and away, and arrive at meaningful conclusions. And that's how the gravitational waves got detected a few months ago. That made a lot of news in all around the world. And the traces of water on Mars was made using X-ray spectroscopy of radiation that's reflected from Mars. So all these are again really sophisticated technologies using computers and reflective surfaces, radio waves, and to make observations. So these are again sophisticated technology that can make observations, but these are again fitting as gadgets around our senses. So whatever we observe, whatever senses we have to be, these just enhance them and make them see farther and better. So that's what happens. But even this is not sufficient to make some observations. Some observations has to be made. There's only one place where you can make these kind of observations, and that's inside your head. So you need to meditate. If you want to know the real truth, real fact, you need to dwell inside your mind and see what's going on. So this is the idea of abstraction. So you start thinking abstractly. That's only way how you can separate out all this intertwined phenomenon. They do not happen individually or sequentially. They're twined around each other. So this kind of phenomenon the riddle be solved only by using abstract principles. And Newton started off with describing the laws of motion using an abstract entity called a point mass. This point mass doesn't exist in reality. It exists only in theory within the abstract mind. And this point mass could be described as something that has a mass, that does have a mass, but that's inobservably low. It's very, very small that it could not be observed at all. And doesn't have a shape, nor a size, nor a structure, nor any associated subparticles. Now we already know that this cannot exist, because even subatomic particles, we have been consistently breaking it down further and further to arrive at even lesser degrees of atomicity. So what happens here is that you assume the existence of such a thing to reason out on the nature of motion. So there is a point mass existing, because with point mass you don't have to worry about this thing, the molecular motion. So you can say that this is at rest and you can get away with it. But you say the refrigerator at rest, I would still argue that the molecules are in motion. Now what about this planetary motion? How do you get away with this? What about the point mass that's set out on, again, sitting on a planet somewhere in the universe? It has to be somewhere in the universe, isn't it? Now how do you work that out? On the universe itself, there is no place that is without motion. because the planet is in motion, and every star, every single asteroid, or even the solar system itself is in motion. The sun is whirling around the galaxy at a great speed, and the galaxies themselves are spinning or moving, or something is happening all the time. So what Newton said is that the same thing that I say here, because you are on the same planet, because you rest on the same surface of the house as this refrigerator, with reference to you, this fridge doesn't move. I would not say it to be false if you say the fridge doesn't move. Of course, I ignore the molecular movement here. So, with respect to a point of reference, we can say that this object doesn't move. And this point of reference is again an abstract thing. Because in reality, even if I say something as relative to the point of reference of myself as an observer observing this fridge from the same room, there would still be minor aberrations, minor differences in my movement vis-a-vis the fridge that can cause things to go wrong. We cannot. It can again exist only in theory, but such a relativity exists in broad terms. We cannot reproduce it in scientific accuracy, but it exists. So we're just making it more precise here in our abstract mind. So we introduce something called an origin here. We call this an origin, and we say with respect to this origin, this is at rest or this is at motion, and this is a point mass, so I don't have to worry about all its components or other forces acting on it. You don't have to worry about any of this. So now this origin is introduced. So this is again an abstract concept. Now instead of resting with a point of reference, I now expand it a bit further and introduce the coordinates x, y, and z. Now this is a three-dimensional coordinate system that was introduced by Descartes, and Descartes predates Newton. And this theoretical three-dimensional space can be used to describe, using three coordinates, any particle in that space. For instance, I can probably describe this particle as 2, 4, 0, x, y, and z coordinates respectively, with respect to the origin here. If I move the origin, value changes. So I have, instead of talking about a point of reference, I have something called the frame of reference. So this frame, this goes on till infinity and this infinity. So the moment I fix the origin here, I can always draw three axes, and every position in space can be described by three numbers here. And these three numbers are sufficient, complete, to describe a point mass at any around within this system here that lives in my abstract imagination. That's because it doesn't have anything else to describe itself by. It doesn't have size or shape or weight or anything. So position is the only attribute it has, and these positions can be reduced into three attributes here as coordinates, and I describe it in this final. So I can have one more dot here, and this is probably 1, 5, 0. Again, one more particle, one more point mass here. So this way I can endlessly go on describing a number of point masses that exist within this frame of reference, which I will now call the inertial frame of reference. Actually, many people think the idea of relativity originated with Einstein, but it's even the Newton's first law dwells a lot on relativity. See, right here we talk about things that are related because we see the problem of relativity, of the problem of handling an independent observations. That's the reason why you use an assumed plane of reference or frame of reference. This is the inertial frame of reference for observations in a relative manner. So now, using these two abstract entities, I can go on describing a lot of particles. Now, it doesn't happen that all the particles are at rest. Some of them are moving, probably along a combination of these axes, or probably along one axis. For simplicity's sake, we assume something is moving along the x-axis, and as we start observing at the time t0 through t1, t2, t3, and t4, we see that the position of this particle changes. changes in a steady manner. It starts with 1 1 0, then again 1 2 0 2 1 0, 3 1 0, 4 1 0, and so on in a steady manner. Now do I say that the system under observation changes? Now I will not say something to be changing here, because something is moving. That's different from something is changing. Whatever is at rest is at rest. Whatever is moving, the moment, the arbitrary time at which I set off into this meditative state and started observing this motion of this particle, it was moving. I cannot say it was at rest and then start movement. And at some arbitrary point, I'm going to cease observing, cease looking at it at all, and start working on conclusions. And at that point, that would still be moving and maybe beyond. Something was happening before I started observing, and something is going to happen beyond my observations. I would not say that something has changed. Something is moving, but it's not changed. So probably Newton's first law could also be stated like, in an inertial frame of reference, nothing changes. Nothing changes. In an inertial frame of reference, nothing changes. Things that move keep moving, things at rest are at rest. Whatever I see here about the ball slowing down or the fridge jerking into motion once the power comes through, are all a combination of phenomena, not phenomenon in its refined originality. If you really want to look at phenomenon's refined originality, that's what you see here. So you see here is nothing changes except time. As time goes on, nothing changes. Things in motion remains to be in motion, and they move along in the same direction. They don't even change direction. They don't even change velocity. The moment they change velocity, then it's acceleration, and that's when change comes in. And that's not within the purview of the Newton's first law. We have to go into the second law to have a look at it, which we will in the next recording.